when we want to measure how a function changes not just strictly along the coordinate axis, but in any arbitrary direction we choose. We use the directional derivative. While partial derivatives give us the rate of change when we move strictly parallel to the x-axis or the y-axis, the directional derivative allows us to calculate the slope when we move along any unit vector u, which has components u1 and u2. Formally, the directional derivative of a function f of x and y in the direction of the unit vector u at a specific point x0 and y0 is defined as the limit as h approaches 0 of the fraction, where the numerator is f of x0 plus h times u1, y0 plus h times u2 minus f of x0, y0, and the denominator is h. Let us look at a concrete mathematical example. Suppose we have the function f of x and y equals x squared plus 3 times y squared, and we want to find its rate of change at the point 1, 2, moving in the direction of a vector that makes an angle of pi over 3 radians with the positive axis. First, we find our unit vector component, where u1 is the cosine of pi over 3, which equals 1/2, and u2 is the sine of pi over 3, which equals the square root of 3 over 2. Next, we recall that for a differentiable function, the directional derivative can be computed efficiently by taking the dot product of the gradient vector and our unit vector. The gradient of our function at the point 1, 2 consists of 2 times x in the first position, which evaluates to 2, and 6 times y in the second position, which evaluates to 12, giving us the vector 2, 12. To find the directional derivative, we take the dot product of the gradient vector 2, 12 with the unit vector 1/2, square root of 3 over 2. This gives us 2 times 1/2 plus 12 times the square root of 3 over 2, which simplifies to 1 plus 6 times the square root of 3. Let us consider a second example in 3-dimensional space. Suppose we have a function of 3 variables, g of x, y, z, defined as x times y squared times z cubed. We want to find its directional derivative at the point 1, 1, in the direction of the vector pointing from that point toward 2, 3, 2. First, we normalize our direction vector by finding its length, which is the square root of 1 squared plus 2 squared plus 1 squared equaling the square root of 6. So our unit vector has components 1 over the square root of 6, 2 over the square root of 6, and 1 over the square root of 6. Next, we compute the gradient of g by taking the partial derivatives with respect to x, y, and z. The partial derivative with respect to x is y squared times z cubed. The partial derivative with respect to y is 2 times x times y times z cubed. The partial derivative with respect to z is 3 times x times y squared times z squared. Evaluating these partial derivatives at the point 1, 1 gives us 1, 2, and 3, meaning our gradient vector is 1, 2, 3. Finally, we compute the dot product of the gradient vector 1, 2, 3 with our unit vector, yielding 1 times 1 over the square root of 6 plus 2 times 2 over the square root of 6 plus 3 times 1 over the square root of 6 plus 3 times 1 over the square root of 6, which equals 8 over the square root of 6. This demonstrates how directional derivatives provide a precise mathematical tool to measure change along any arbitrary path through a multi-dimensional space.